Let us look at the function f from r to r given by f of x is equal to x squared. And I'm interested at its behavior near the point root 2. Okay, so often you would have seen root 2 getting expressed as 1.414 or something like that. You know that it's not exactly equal to root 2 because root 2 is irrational while 1.414 is rational. Now if we take root 2 squared, clearly what you should get is 2. However, if you take 1.414 square, what you get is not equal to 2. You get some error. That means it's little bit away from 2. So what you want to do is that how far away from 2 it is and compare it with how far x was from root 2. That means how far 1.414 was from 2. So what am I doing? I'm comparing the error in the value of x to the error in the value of f of x. That's what I want to do. So for a small error in x, how much error do we get in f of x? So this is what we are going to now see. Let's do this by looking at some values of x and looking at the corresponding values of x squared. So let us look at various values of x, the corresponding values of x squared, and the error in the value of x squared. That means what I am doing is, more precisely what I am doing is, I am looking at the value 2 minus x squared. That is the error that I am getting, correct? So let's say that suppose x was equal to 1.4. Then x squared will be 1.96. So the error you have is 0.04. Instead, if you had 1.41, then the x squared value is equal to 1.9881. I had calculated it before. So if you do not trust me, you can check it using a calculator. And the error now would be equal to 0.0119. Notice that the error in the value of x squared has also decreased when the error in the value of x decreased. Okay. Now if you can look at 1.414 and look at the corresponding value of x squared. What would be the value of x squared for this? So what is 1.414 whole squared? That's equal to 1.999396. And the error is equal to 0.000604. Continuing this process, we can fill the table in the following way. What do we see from this table? We see that as x gets closer and closer to root 2, x squared gets closer and closer to 2. Or more precisely, 2 minus x squared is getting smaller and smaller, it's going to 0. Now, that's all we can see if we just look at one function. So what we will do is we will look at another function now. The next function we will look at is x power 4. I could have taken x power cube, but x cube of that means root 2 cube is not a number that we know. But root 2 power 4 is nothing but 2 square, which is equal to 4. So we can easily calculate the error. That is why I am taking x power 4. So let us look at the function x power 4. Okay, and now I have to look at the error in the value of x power 4 for these various choices of x, right? That's what I have to do. So look at the error in the value of x power 4. What do I have to do? I have to look at 4 minus x squared. Sorry, I mean 4 minus x power 4 actually. That's the error, right? So let us see what are these various values again. And looking at these values, we can again fill the following table. So for the same value of x, if we compare the errors in these two different functions, we will notice that the error for this, that means x squared, the function x squared, is much lesser than the error for the function x power 4. More precisely, you can see that it's 4 times. It's roughly 4 times. The error is 4 times for the function x power 4. And it can be seen not just there, like 1.5 and 6. So that's roughly 4 times. 4 and 1.5, which is like 0.16 would have been 4 times. So that's also 4 times. Moreover, if you actually notice the ratio between these two is not exactly 4, but it's close to 4. The ratio between these two is also not exactly 4, but close to 4. But the ratio between these two, the second one, the ratio between these two is actually closer to 4 than the ratio between these two. And the ratio between these two will again be closer to 4 than the ratio between these two. So as you proceed below, the ratio is getting closer and closer to 4. That is what is happening. So what have we seen here? If there is some error in the input, the error in the output of the function x power 4 will be higher than the error in the output of the function x squared. So in some sense, the function x power 4 is more sensitive to error in input. Okay, and here we needed two functions, x squared and x power 4, and compare them to see this difference. But however, we could have done something else actually. We could have compared it with the error in the value of the input itself. That means instead we could have compared 2 minus x squared with root 2 minus x, and 4 minus x power 4 also with root 2 minus x. That way we do not need these two functions. Why did I not do that? I did not do that because it's very difficult to write root 2 minus x, because I cannot write the explicit value of root 2 in terms of decimals. So I cannot do whatever I did here. That's why I did not do this. But ideally it is actually, without using these two functions, I can work by just comparing it with the error in root 2 minus x. What we observed is that if we look at the ratio x power 4 minus 4 divided by x square minus 2, then as x became closer and closer to 2, then this ratio was converging to a constant which was equal to 4. This was kind of an observation, okay? And this meant that the function x power 4 was more sensitive to error in the input than the function x squared. However, we wanted to now express this as a property of the function alone rather than in comparison with another function. To do that, we had the idea that we could instead look at the ratios x square minus 2 divided by x minus root 2, and similarly x square minus 4, x power 4 minus 4 divided by x minus root 2. We could have looked at these ratios. But if you look in the earlier case, that means this case, notice that the ratio x power 4 minus 4 by x square minus 2 was itself not giving something interesting. When you took the limit as x tends to root 2, it was giving us something more interesting. So perhaps we should take the limit x tends to root 2 here as well. Okay, and we expect that this limit exists. If suppose this limit exists, then that limit can be taken as a measure of the sensitivity of the function to error. And what is the limit actually doing? See, the limit is saying that you can take the error to be as small as you want. Okay, you take a very small error in input and see what is the error in the output. And of course, you take the ratio of error in output to error in input. But what we are saying is we are not interested in what happens if the error is large. That is not so important. What is important is what happens when the error is really small. At that situation, what is the ratio? That's what we are looking at. And that is what is captured by the limit part. Okay? And this is the intuition behind derivatives. Let us get into a formal definition in the next video.